This is my submission for exam chapter 27. Part A states an electron with charge of negative 160 times 10 to the negative 19 coulombs moves at 2.20 times 10 to the fifth power miles per second of speed through a uniform 1.75 t magnetic field that points in the plus y direction. The velocity of the electron lies in the xy plane and is directed at 60 degrees, not 60 degrees Celsius, 60 degrees for an angle, to the plus x axis and 30 degrees to the plus y axis. Find the magnitude of the magnetic force on the electron. So for this, we're going to utilize the formula to find the magnetic force. So this would be F is equal to Q for charge times the speed times V sine of the angle. So then when we plug our values in, this would be negative 160 times 10 to the negative 19 for our charge. Our speed, 2.20 times 10 to the fifth power times B for our magnetic field, 1.75 times sine of our angle. In this case, we're going to use 30 that we were given. So when we plug this into our calculator, we get negative 3.8 times 10 to the negative 14n, or 3.8 times 10 to the negative 14n for our answer. Part B is asking to find the direction of the magnetic force on the electron. So when using the right-hand rule, we would point our finger in the negative x direction and the middle finger towards the positive y direction, because the magnetic field goes in the positive y direction. So the thumb points in the negative c direction, which tells us the direction of the magnetic force of the electron. So this would be, for part B, negative c direction. Part C is asking a charged particle moving in the presence of 0.750 T magnetic field experiences a magnetic force of magnitude 2.50 times 10 to the negative 10 n. The particle is moving at 1.95 times 10 to the fifth power meters per second at an angle of 36.0 degrees to the direction of the magnetic field. Find the magnitude of the charge on the particle. So we're going to use the same formula. F is equal to Q times V times B times sine of the angle. And then we're going to rearrange this to find the charge. So this would be equal to Q, and then F divided by V times B times sine of the angle. And then this is equal to 0.750. Oh no, this is equal to 2.50 times 10 to the negative 10. And then we divide by our given 1.95 times 10 to the fifth power, our 0.750 times sine of the angle that we were giving, 36, and then all of this is equal to 2.91 times 10 to the negative 15 C. Part D states a particle charge 3.20 times 10 to the negative 19 C with velocity of 3.75 times 10 to the fifth power meters per second is in the presence of a B field with only a Z component. The magnetic force on the particle is 2.10 times 10 to the negative 15 n in the negative y direction. Find the magnitude of the B vector. So for this, we're going to use the same formula. F is equal to Q times V times B times sine of the angle. And then here, we're going to move things around. And then we also have to do a cross, basically what you do with vectors. What's that word? Basically like cross multiplying, like using the little grid to find these answers. So this would be V times B is equal to F divided by Q. And then we're just gonna plug and move things around here. V is our speed, so 3.75 times 10 to the 5th power is equal, let's multiply by B. Multiplied by B, and then this is equal to negative 2.10 times 10 to the negative 15, which was given to us, and then 3.20 times 10 to the negative 19, which was also given to us. So let me think here. This will be equal now to negative 3.75 times 10 to the 5th power, and then this is y now, and then this is equal. Now we're gonna divide this to negative 6.5625 times 10 to the 3rd power y vector. And then we're just going to solve for, we're gonna move, like, basically we're just gonna use the units to find B. So this will no longer be y, but it'll be V. So this would be 3.75 times 10 to the 5th power B is equal to, when we divide this, well, we already divided it, so this would be equal to 6.5625 times 10 to the 3rd power. Our y goes away, and then we divide these two, and we get 1.75 times 10 to the negative 2t. So that is our answer for part D. Part E is asking us to find the direction of B. So same thing as with part B, we use the right hand rule and we determine that this is going in the direction of positive C. So that is our answer for part E. For part F, we are asked, highly ionized iron atoms are found in the sun's outer atmosphere or corona. This is so cool because we just had a solar eclipse, so whoever had a chance to see the corona, I'm jealous of you because I didn't get to see it. One such ion has lost 13 electrons and so has a charge of positive 13. E is equal to positive 2.08 times 10 to the negative 18C. This ion experiences a magnetic force of 2.30 times 10 to the negative 15N when it moves at 7.30 times 10 to the 3rd power meters per second in the XY plane 36.9 degrees from the positive x and 53.1 degrees from the positive z. The magnetic field is in the positive z direction. Find the magnitude of the magnetic field. So here, once again, we're going to resort back to our magnetic force equation. So this would be B times Q. I'm just going to write it down a little bit differently in order to solve this problem. So this would be B times, magnetic force times our charge times our speed times our sine of our angle. And then we have our F here, right? So then we want to set this equal to 0. And then F would be dividing with all of our values here. Well, actually, no. Wait a minute. We're looking for B. Okay, so yeah, we're setting this up like this. A little messy, but whatever. So our F is given 2.30 times 10 to the negative 15 divided by our charge 7.30 times 10 to the third power. Then the 13, because 13 is equal to the 2.8, so we're just going to add it in there. And then 1.60 times 10 to the negative 19. And then sine of 53.1, that's the angle we're going to use. And then all of this is equal to, all of this is equal to, because we're looking for B. All of this is equal to 0.189 T. There you go. 0.189 T. And that is our answer for part F. For part G, we are asked to find the direction of the force on the ion. So once again, we resort to right-hand rule to find the direction, and then the direction from the right hand rule, we determine that it's going in the negative y direction. So that would be our answer for part G. Again, this is Victoria Tencio, and this is my submission for chapter 27 exam. Thank you.